So yeah, DEF CON is a long-standing tradition, and you know, if it's a speaker's first time on stage, then they do a shot. So it's not about alcohol, although, you know, yeah, it's a tradition that is intended just to honor our speakers and DEF CON, you know, from times of yore. So anyway, this is Matt Wixie, and he's going to do a shot with us. Cheers. All right, so please welcome Matt Wixie.
Hello, DEF CON. So this is See No Evil, Hear No Evil, hacking invisibly and silently with light and sound. My name is Matt Wixie. I lead the vulnerability research function on the pen testing team at PwC UK. I also run something called the Dark Art Lab, which is a research blog looking at the more kind of esoteric aspects of security research. I've been at PwC for about a year. Prior to that, I worked in law enforcement in the UK for about 8 years, leading a technical research and development team. So today's talk is split into 4 parts. First, I'm going to show you 3 custom tools I've developed to use light and sound to jump air gaps. I'm then going to talk about laser microphones, 2 different kinds of infrared motion detectors and different ways you can disrupt and disarm them. Part 3, BANTs. I'm not sure if that term has made it out of the UK, but it roughly translates to lulls. So it's kind of stuff I've found during the course of the research that has made me laugh more than anything else, rather than kind of being of practical use. And as you'll see throughout this talk, that's quite a low bar, but hopefully you guys will enjoy it as well. And then I'm just going to sum up and give some ideas for future research. So a couple of disclaimers. The views and opinions in this talk aren't necessarily those of PwC. All the content's for educational purposes only, so please check legislation, get permission, and so on. This presentation isn't about exploiting vulnerabilities per se. It's about manipulating the inputs and outputs of a system in order to have a desired effect. And lastly, I am definitely not an electronics expert or a physics expert at all. In fact, I've only been in security for about 6 or 7 years. My bachelor's degree was in English language and literature, which has been really helpful. So just to give you an idea, I kind of regularly still poke myself in the eye with resistors and burn myself with soldering irons, and I see magic smoke so much it's not even magical to me anymore. It's just I call it routine smoke. So this is where I am on the Dunning-Kruger curve, if you guys are familiar with this. So I don't want you guys to think that I'm kind of presenting myself as an expert on this stuff, but what I'm going to do at the end of the talk is put my Twitter handle up on my email address, and please do get in touch if you think I've got something wrong or there's something that could be improved, or you've got any ideas or suggestions. That would be great, because that's what DEF CON is about at the end of the day, right? So let's jump straight into it. So the first thing I want to show you is this. This is an example of Li-Fi, data transmission through light. In this case, the data is music. And this is adapted off a schematic on GitHub, and the link to that will be in the references part at the end of the deck. But it's basically what we've got here is a phone that's playing music. The headphone output goes to a breadboard of LEDs, which are going to modulate the music data that's going through it. And then you have a photodiode hooked up to a speaker that's going to play the music. Yeah, so that was my impression when that actually worked for the first time. And then I did the same thing with infrared LEDs as well. So exactly the same setup, even the same song. It's just infrared LEDs instead of white LEDs that are modulating. So that kind of got me thinking about air gaps and different ways you can jump air gaps. And I'm going to assume that everyone here is kind of familiar with the concept of an air gap. There's been a lot of research on how to jump them, and they all come with caveats. So the first caveat is that we assume the attackers will manage to infect at least one host with a bit of malware, that the attack has physical or near physical access to that infected host, because we're talking about quite primitive inputs and outputs to a system. So we're talking about like heat, sound, light, EM radiation, that kind of thing. And then linked to that, the exfiltration of air gap systems is going to be really slow, and it's going to be quite small pieces of data, because typically we're talking about 2-bit channels, so high or low states. So this is some of the research that's been done in this area. You guys will be familiar with a lot of this already, probably, all the way from Van Eck phreaking back in the 70s, which is EM radiation from CRT monitors. There's been some great work done by guys at Ben Gurion University in Israel on jumping air gaps, particularly using heat, Visibly, which encoded data as a kind of QR code, flashed it up on the screen, the attacker would then film the screen and be able to decode it. And Hassan and others in 2013 gave a really good overview of some of these techniques. And one thing that they proposed was using ambient light sensors for mobile devices to be able to control smartphones by flickering overhead lighting, that kind of thing. So the first technique I want to show you is using ambient light sensors. So ambient light sensors are essentially hardware components. They're found in the frames of laptops, smartphones, monitors, that kind of thing. And they're normally photoresistors, photodiodes, something like that, that increases or decreases resistance according to the amount of light that hits it. And the idea is that you adjust screen brightness according to the amount of ambient light, so it's quite a benign thing to have. And you can interact with it programmatically through the Windows API. So my plan was to create malware that could read in light intensity values from an ambient light sensor on a Windows workstation, and then execute different commands according to the amount of light that was hitting the ALS and the kind of changes in changes in intensity. So a couple of problems is that you have to try and make this like a covert activity, because you can't just shine a massive flashlight at a laptop. And you need some kind of exfiltration capability as well, right? Because being able to control malware is fine, but for an air gap system, ideally you want to concentrate on exfiltration. So I'm going to be brave and try and show you a live demo of this. Okay. So I've got a laptop here that's got an ambient light sensor. The ambient light sensor is just here. And what I've got here is an infrared torch. So if I turn this on, you should be able to see anything other than like a red glow. But for unfiltered cameras, they'll be able to see that. So I'm going to run the malware on this laptop and then introduce high values through the ambient light sensor. And that then pops up calc on the screen. Okay, so in terms of exfiltration, optical channels for air gaps are quite difficult optically. There have been some things suggested, so Visibly, like I mentioned earlier, that relies on the attacker having a camera inside what is probably a secure area. So I came up with this instead. So the idea here is that the malware, when it wants to exfiltrate data, it will read in a file, convert it to bits, and it will then make very subtle changes in the screen brightness to represent that, which can be then picked up by an external sensor. So the easiest way to make screen brightness changes is with WMI. Unfortunately, that requires admin privileges. However, changing gamma values in displays doesn't. So you can use a set device gamma ramp and the Windows API, and you can make very, very small changes in the gamma value of a display. So the device I've got here is a light to frequency converter, and this is much more sensitive than a typical photodiode or photosensor. It can actually pick up changes in the bioluminescence of bacteria. It can read light intensity changes through your hand, and it's connected to an Arduino Nano here. So what I've got here is a circuit connected with a micro SD reader writer module. And I'm just going to do a test of this exfiltration function. So the malware is going to read in a file, and it's going to make very small changes to the gamma value of the display. What the malware actually does is it takes like a baseline before exfiltration, then it makes changes, increases or decreases according to whether it's a 1 or a 0, and then after exfiltration is finished, it will return it back. So you might be able to see that, the very kind of slight changes there, but from the attacker's point of view, it's actually quite obvious whether it's a 1 or a 0 that's being transmitted. And then what you can then do is demodulate the data and retrieve the original bits. And that's not particularly covert, kind of just plonking a breadboard down to a screen. So this is a more covert application. So what you have here is the same light sensor, light to frequency converter, an Adafruit Flora board, so they're conducted with a conductive thread. And then you have the same SD reader writer as well. So the idea is you could exfiltrate data, or an attacker could exfiltrate data, just sitting in front of a screen and wearing that tie. So the second thing I want to show you is Dreadphone. So Dreadphone is command and control using near-ultrasonic sounds. So by near-ultrasonic, what I mean is sounds that are typically not able to be heard by most adults. So the theoretical range of human hearing is 20 hertz to 20 kilohertz. In practice, most adult humans can only hear up to about 16 kilohertz. So 16 kilohertz to 20 kilohertz is like near-ultrasonic. And whilst most adults can't hear that, it's perfectly within the capabilities of a normal laptop sound card, speaker and microphone to transmit and receive audio in that range. So there's been previous research on this. Tosted and others, and Hansbach and Gertz did something similar. One problem they've come across is this. So this is a recording of near-ultrasonic sounds being played. So while you can't hear the tones there, what's actually happening is that there's electrical discharge on the sound card, which makes those kind of clicks and pops. So what I did with Dreadphone was I pre-prepared 16 wave files. Each one represents a different ultrasonic tone in increments from 18.5 kilohertz up to 20 kilohertz, so 16 in total, each one representing a hex character. I applied multiple fade-ins and fade-outs to those, so it kind of smooths the input into the sound card, and then amplified it, and you end up with this. So this is Dreadphone running on 2 laptops. This is the victim, and the attacker is here on the left. So this is monitoring the microphone input. So what the attacker is going to do here is just tell the victim to pop calc, which means it's going to send it a sequence of those pre-prepared wave files, and the victim then executes that. Okay, so the next thing is exfiltration. So this is a text file. So Batman would be a really different movie if Bruce Wayne was actually true to type and communicated with people at 45 kilohertz. So the attacker is going to exfiltrate this text file. So he's just going to send the exfiltration message. And I'll stay with the attacker here, and what you'll see is the different tones start to come back. Now, there is a case study of this technique being used in the wild. I haven't got a copy of the malware, so I haven't been able to verify it, but Bad BIOS, you guys heard of that? So that, whilst it infected the BIOS of machines, it also communicated with other infected hosts. There you go. Using near-ultrasonic tones. So Dreadphone's fine for like small bits of data and small strings and stuff like that, but if you want to exfiltrate more content, say images for instance, you're a bit more limited. But you can actually use a technique that's been used in popular music before, and it involves spectrograms. So a spectrogram is a visual representation of the frequencies in a piece of audio. And what these musicians have done is they've read in an image file, they've iterated through the pixels, got the pixel values, and then they've written out frequencies to a wave file that correspond to those pixel values. And when you view the audio as a spectrogram, you end up with an approximation of that original image. So in this case, you have a face on the left and a cat on the right. So these are both examples from popular music. So let me try another demo. So let's say I have an image like this that I want to exfiltrate. This is the spectrogram tool that does that. So it reads in the image, and then you can specify a minimum and a maximum frequency. So I'm staying with near-ultrasonic again. If I generate that, it writes out a WAV file. If I try and play that WAV file, you shouldn't really be able to hear anything unless you've got really good hearing or you're younger than I am. Some of you might be able to hear it. But if I view that in a spectrogram, you can recover the original image. Now, there are tools out there already that will let you do this, so coagular, spectrology, that kind of thing. What spectrogram also does is it lets you merge your secret file with a legitimate audio file. So in case you have got your kind of younger people working in your environment, they're able to hear that. So I've got a normal WAV file here. So it just plays kind of ordinary music. And I can merge my secret file with that. And that writes me out a new WAV file. If I play that, you just hear the ordinary music. You can open that merge file and still recover the original image. Okay, so in terms of mitigation for this kind of stuff, for jumping air gaps in general, you're looking at things like Tempest standards, removing or disabling ambient light sensors if they're not required or covering them up. Privacy filters for laptops do a really good job of muting screen brightness changes. And in terms of the ultrasonic stuff, you could look at things like white noise or ultrasonic detectors, but ultimately, if you've got any kind of input and output to a system that's not necessary or not integral to the operation of that particular piece of equipment, you're probably better off just disabling it. So part two, surveillance and counter-surveillance. So the first thing is a laser microphone. Just a quick hands up, who's heard of a laser microphone before? Okay, quite a few people. So for those of you who haven't, I'll just quickly explain what it does. So imagine that you're doing surveillance on a group of people across the street from you. And those people are behind a window. Let's say the glass is soundproofed, so you can't hear anything. Let's say they've closed the curtains so you can't video them and do lip reading, and assume you don't have any bugs or anything in the room. What you can do is use a laser microphone. So you shine a laser at the window and you capture the reflected beam with a photodiode or a photosensor. So what's happening is as those people in that room are talking, the air is vibrating, it makes the glass in the window vibrate, which makes your reflected laser beam shift slightly. And as that moves across the surface of your photodiode, it will cause shifts in voltage, which can then be converted back into sound. So on the right here, I've got a really cheap laser module that's hooked up to a 9-volt battery. And on the left, I have a photodiode. This is actually adapted from a circuit that did something else. The output goes to a 3.5mm audio jack. So to demonstrate this, so I have the laser, I've got the listener hooked up to a speaker. The laser is firing at a phone that's playing music very, very quietly. Taped to the back of the speaker is a bit of reflective material. And at the moment, there's a bit of obstruction between the reflected laser beam and the listener. If I remove that, So that's obviously like a really cheap, really simple model, and that only costs like £25, the whole kind of setup. If you obviously had a bit more budget, you could use like interferometry. You could experiment with using infrared lasers to make it more covert, because nothing says I'm using a laser microphone like shining a really highly visible laser. You could kind of filter out interference, use a shroud, that kind of stuff as well. Okay, so moving on to sniffing, analyzing, cloning infrared. So I imagine a lot of people here will have done or will have experimented with like clone and replay attacks using an SDR with RF signals. And infrared's very similar. So with infrared signals, assuming they're like fixed codes, they will use things like biphase mark encoding, Manchester encoding, that kind of thing as well. They use a carrier wave at normally 38 kilohertz, but it can be other frequencies as well. So we need a way to listen to the signal, then a way to analyze it, and then a way to replay it. And if you guys are interested in infrared, there's a really great talk from DEF CON in 2005 by Major Malfunction, who found a way to compromise hotel payment systems by messing around with infrared TV remotes in hotel rooms. So the first thing you could do is just use an RTL SDR. So these things still have an infrared sensor in them that you can actually use to sniff infrared signals. It just returns you like the raw pulse data. So it's completely undercoded, but you could do that. You could use a dedicated infrared receiver component and an Arduino, and then use the IRlib library. And the nice thing about this library is if it's one of kind of 8 or 9 popular consumer protocols, it will actually tell you what protocol it is and decode it for you. So in this case, this is the standby signal for my TV remote. So it tells me it's using the NEC protocol, and it then tells me what the value of that code is. And then you could also use the listener for that laser microphone. So that will do it as well. And then you can inspect the signal visually, which is quite nice. In terms of replaying it, if it's a known protocol like NEC or something like that, you can just play it back. So in this case, I've used the IR remote library. You can just play it back with the normal consumer protocol. Like RF, however, if it's unknown, then you have to replay the raw array that you've managed to sniff. So applying this practically to motion detectors. So the first thing I'm going to talk about is a passive infrared motion detector. So these have a passive infrared sensor on them that respond to changes in infrared radiation, i.e. Body heat. So there was a talk, a Black Hat 2013, USA, by Porter and Smith, where they talked about different methods to defeat physical security, and they mentioned passive infrared sensors. And you can do things like move really slowly so that changes in body heat aren't registered by the sensor. You can coat yourself in a reflective material. It's not the most practical approach, but it works. Or you can like overwhelm the sensor with heat, so with like a flame. So I think in their talk they used a lighter to do it. So here's an example of a passive infrared motion detector. So the grey sphere on it, that's the actual sensor itself. The red window to the top, that's actually a receiver for that remote control. So the remote control is used to arm or disarm the main unit. Quite why they've used infrared to do that, I don't know, as opposed to RF. And then on the right is a circuit board that I can use to do a simple clone and replay attack and just clone the disarm signal from that remote. So it's now armed, I've just tested it works. And then I can use my evil device to just clone the disarm signal. And that's now disarmed. So there's nothing kind of particularly innovative or interesting about that. It's just a normal clone and replay attack. I suppose the one thing that is interesting is it's infrared. But there's 2 big flaws in this approach. And the first is, how do you get the disarm signal in the first place? Assuming it's, because it's infrared, you have to be quite close to it. So you're stuck with having to like have a device in the vicinity or steal a remote somehow and capture the signal. And the second problem is, how do you get close enough to disarm it once you've got the disarm signal without setting off the main unit? So I bought 9 of these that are manufactured by the same manufacturer but sold under different brand names. And I captured the signals from the remotes. And here are the signals from the first 6. Okay, so straight out of the box, regardless of what main unit the remote was first used with, it will arm and disarm any main unit. So here's all 9. So if I just pick a remote up, and then pick another one up, and I can disarm all of them. So I'm almost like embarrassed to present that at DEF CON. Now, so that's the first problem taken care of. How do we get the disarm signal? The second problem, how do we get close enough to the main unit to disarm it without setting it off? Here's the first solution. So this is drone to clone to pwn. This is the disarming circuit powered by the drone's internal USB port. The reason you can use a drone is because the lithium battery in it doesn't get hot enough to set off a motion detector until it's been in the air for about 45 seconds. So here's the alarm in the foreground. You can see I've dressed up for this video. So if I arm this and then try and walk up to it, it detects me. So you'll shortly see that my drone piloting skills are about on a par with my fashion sense. Okay, so I'm going to fly the drone over, and it won't set it off, but it will disarm it. Okay, second solution, phone to clone to pwn. So this is using an Adafruit GSM breakout board. This is heavily based on Sammy Kamkar's Ding Dong Ditch, or Digital Ding Dong Ditch, if you've seen that. Some slight modifications, so obviously it uses infrared rather than RF. It also doesn't use interrupts, it just uses a timed loop, and it deletes text messages off the SIM card once they've been read. So the idea is you would hide this or pay someone to hide this near an alarm during the day when it's deactivated. Then after hours, when the system is armed, you can just send a text to a number containing a certain string, and it will then disarm it. Okay, so as usual, the first thing I'll do is arm the main unit and then just test it. Okay, and I'll just look quickly at the Arduino sketch, which is just checking for new messages every 5 seconds on that SIM card. So I'm now going to send a text to the number that's on that SIM card, and in this case, the string that the sketch is looking for is new phone, who dis? And then just looking at the sketch, so just to make sure, so it reads the text message, sends a signal, and then deletes the message from the SIM card. Now you could combine both of those together and do phone a drone to clone to pwn, but that would just be absurd, so I haven't done that. Okay, the next kind of motion detector is this. So this is an active infrared motion detector. So the idea here is you have 2 components, a transmitter and a receiver, and the transmitter is constantly sending a pulse of infrared signals to the receiver. And if the beam's broken, then the alarm sounds. And if you continually move the transmitter away, then the alarm will just continually sound until you clone the signal from the transmitter and just put it right next to the receiver. Okay, so in terms of mitigation for these kind of attacks, so for laser microphones, You can get devices that vibrate the glass on windows to try and disrupt laser mics. I'm not sure how effective they are, but things like wire screens and coverings on windows, as you've seen with the infrared torch that I use, you can detect infrared light if you're using an unfiltered camera, so you could use that to detect infrared lasers. Double glazing or curved glass can cause issues with laser mics, as can other environmental conditions like rain and snow and that kind of thing. In terms of alarms, ideally you want to try and disarm with physical keypads. Not that that's perfect, but it's better than remotes because the signals can be sniffed. And if you do have to use remotes, you want to go for ones that use like tried and tested encrypted rolling code algorithms and that are paired uniquely to a device. You wouldn't think you'd have to say that explicitly, but yeah. Okay, so last part is BANTs. So the first thing I want to show you is speech jamming, or delayed auditory feedback. So this is a technique that's been around since the 50s. It's actually originally used to help people who stutter. The idea is you introduce a latency between someone speaking and them hearing themselves speak. And when used with people who stutter, it enables them to speak more clearly. If you use it on people who don't have a stutter, it dramatically inhibits their capability to speak. And it causes like mental stress. So there were some researchers in 2012 who came up with like a hardware version. I built a software version called Doublespeak, and I tested it out on some colleagues because I didn't want to look stupid myself. So what these guys are doing is they're reading a paragraph from a website about delayed auditory feedback while my tool is running on that laptop, and they're wearing a pair of headphones.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between speech and auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between the speech and the auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between speech and auditory perception.
And here's the voice in headphones a fraction of a second later. Some DF devices are hardware, DF computer software is also available. Most delays produce a noticeable effect of between 50 to 200 milliseconds. DAF usage with a 175 millisecond delay has been shown to induce mental stress. Joy, this is stressful.
So on the face of it, that doesn't seem to have much practical application to security. One way that we came up with that you might be able to use it is, say you're on a network and your goal is to kind of sow disruption and discord, but in a very subtle way. You could find out when a very important conference call is taking place and use this and kind of affect the decision outcome of that conference call without kind of having to do anything and too blatant. Okay, next thing, demotivating malware analysts. So this is inspired by Christopher Domas, who's speaking tomorrow, I think. And he came up with this awesome thing in 2015, which was he created fully functioning malware, which when looked at in a disassembler, in a flow graph, represents an image under his control. So he can basically choose the image that a malware analyst has to stare at all day long, which is awesome. So I used my spectrogram tool to come up with something similar, albeit a lot cruder. So let's say you've got malware, and when you run it, it plays really weird music like this. So the first thing you do is disassemble it. In this case, it's .NET, so it's very easy. And you look at what's causing that sound. So in this case, it's a WAV file that you can then extract from the main binary. And you're playing that WAV file and trying to think, what is this? Is it some kind of encrypted communication? Is it trying to exploit something? What is it? And you would spend ages and ages looking at it until eventually it occurs to you to look at it as a spectrogram. And then you see something like that. Okay, do we have any Gilmore Girls fans in the room? Okay, so to give you a bit of background on this, my wife is a huge Gilmore Girls fan. She watched it all when it first came out. They streamed it like 2 years ago, and since then she's watched like season 1 to season 8. I've lost count. And in that time, I've gone from kind of passive indifference and thinking, this is okay, but I can't really see the appeal, to kind of active loathing of this program. So I came up with Kilmore Gilmore, which I think on reflection is probably the best thing I've ever done. So Kilmore Gilmore it's 2 parts. It's a Python script and an Arduino device. Now the Python script uses an open source music recognition library called Deja Vu, which is on GitHub. Again, the link will be at the end of the talk. And what Deja Vu does is it lets you write MP3 files to a database and it fingerprints them, I believe using a fast Fourier transform. And it then compares audio coming into the microphone to what's in the database. So my Python script here is comparing audio coming into the microphone to the database. And if it gets a match for the Gilmore Girls theme tune, it sends a byte over the serial port to the connected Arduino device, which clones the power off signal for my TV. So I have a video of this. Unfortunately, because of possible copyright issues, I've had to mute it. But after the talk, if you look at my Twitter feed, I'll upload it somewhere with a full audio so you can see it. Okay, so this is like the pre-credit sequence, so there's no music yet. So what the script is going to do is just listen to 10 seconds and it will conclude that the Gilmore Girls isn't playing at the moment. Okay, and then the theme tune starts. Okay, and the last thing I want to show you is this. So this is Astro Drone. So this is using echolocation jamming against ultrasonic altimeters in drones. So I've demonstrated it with a Parrot just because I had one handy. It's not picking on Parrot specifically. Other drones with ultrasonic altimeters will be vulnerable to this as well. So the idea with an ultrasonic sensor is it uses echolocation, right? So you have a transmitter that sends out ultrasonic pulses at a particular frequency. They hit an obstacle, get reflected back to the receiver. And based on the width of the pulse that comes back, the navigation board can infer how far away it is from the obstacle. So when you do this with drones, with ultrasonic altimeters, because it's used on the bottom of the drone to figure out how close it is to the ground, 8 times out of 10 it launches it upwards at quite a frightening pace. 2 times out of 10 it tries to sink through the floor because you're making the drone think it's either at maximum or minimum altitude. So there was a talk last year at DEF CON by Lou and others about ultrasonic attacks against autonomous cars, against Teslas. So this is a similar technique, albeit a lot cruder. So first thing I used was this. So this is an animal repellent alarm. So you put this in your garden. The idea is you have a passive infrared sensor. When it goes high, it sends out an ultrasonic tone to scare away dogs and cats and that kind of stuff. When you fly a drone over it, so you notice there that the drone became like completely unresponsive to commands and just refused to land. And in that case, you end up with a broken drone. So that was kind of the first part of this. And then I thought, well, let's try and expand that. So rather than having the drone fly directly overhead, can we come up with something that detects drones in multiple directions and sends out a more powerful signal? So that's a colander, because I ran out of money. And you have 4 passive infrared sensors. There's 2 Arduino Unos underneath, and 18 ultrasonic transducers connected to it. So Infrared's one option, and then I also used acoustic signatures with the Deja Vu library again. So record the sound of a drone flying and then compare the microphone to it. And that works just as well, I just don't have time to show it. But let me show you this one. So. Okay, so we are like doing further research on that at the moment and trying to like test it against different drones, different kind of environmental conditions, different kinds of echolocation jamming, that kind of thing. So you could use this essentially as like a drone repellent. If you wanted to, you could use it as a personal drone repellent as well. Okay, so I think I have about 5 minutes left, so I'm just going to do a really quick summary. If I don't have time for questions, then I'll take them in a hall afterwards, or you can tweet me or email me or whatever. So this is an overview of the research that I've done on light and sound, and you can interpret this in two ways. You can either look at it and think, yes, he had a really careful and comprehensive research plan, or it's something he cobbled together this morning to give his talk the illusion of structure. Either one of those is good with me, but they all kind of do fit into each other. So as an attacker, using light and sound for attacks, pros are they're great for any environment that uses physical security devices, particularly infrared stuff, any environment where there's air gap systems. They're really difficult to detect and to defend against, and they leave very little trace. And you can, as you've seen, do this stuff on the cheap a lot of the time, kind of at home, and test it out. Cons are you need proximity to the systems you're attacking, obviously, subject to environmental interference, particularly things like laser microphones. And the range and power of your solutions are very much going to depend on the resources that are available to you. So in terms of mitigation, definitely the first step is knowing that these techniques exist and that they're out there, and the inputs and outputs can be manipulated. So ideally, if it's possible or feasible, you look to block those inputs, outputs completely. If you can't, you'd have like a reliable failover. And lastly, yeah, clone and replay attacks and jamming, that kind of thing, are as much applicable to light and sound as they are to any other kind of technology. So ideas for future research: exfiltration via infrared is something I've wanted to explore. Acoustic keylogging, which has been empirically proven to work, but I've yet to see like an automated practical solution for it. More work on Li-Fi, and then some more work on drone repellents as well. So hopefully, in terms of how you feel about this talk, you're more on the left than on the right. So just to wrap up, the music credits that we used in this presentation were royalty-free or Creative Commons, so thanks very much to those people for putting that music out there. References, I'll let you guys go through those in your own time. So that's my email address and that's my email address, my Twitter handle. So please do get in touch if you've got any suggestions, comments, feedback generally, criticisms, anything like that. If I've got anything wrong during the talk of this presentation, you can just keep that to yourself. So that's it from me. Thank you very much.